Alright, next let's look at the oscilloscope. So oscilloscopes are another piece of equipment that are used very frequently in electronics labs. Oscilloscopes are very similar to the voltmeter function in a multimeter, except with an oscilloscope it allows you to look at a collection of points rather than just taking a single measurement. So with an oscilloscope you can look at an entire voltage waveform and see how your signal is changing throughout time. All oscilloscopes are designed to measure voltage, but with special probes like this current clamp here, you can use your oscilloscope to take current measurements as well. So some waveforms that you might be interested in looking at are like a clock signal or maybe the ripple on the output of a power supply. Both of these signals would be really hard to look at with a standard multimeter. So all oscilloscopes basically have the same controls. You have your horizontal axis and your vertical axis, and with vertical axis you can scale your signal, and you can also change the offset up and down. And similar with the horizontal axis, you can stretch your signal out or squish it to see more of it. And you can move throughout time of the capture in case you're interested in an event that isn't being shown on the display. So oscilloscopes also have what's called a trigger, and as you can see, this line going up and down is essentially a trip point for a signal. So triggers can be configured both with a trigger level and also a trigger type, which I'm not going to go into the menu, but you can set up to trigger on a rising edge and a falling edge. There's all different sorts of ways that you can trigger on a signal. So what we have here is actually the output of a MEMS oscillator being used as a 54 megahertz clock on a printed circuit board. So this looks like a sine wave, which is not what you would expect for a clock signal. So it's worth mentioning the two specifications that really determine how much you're going to pay for an oscilloscope. So if you can read these numbers here, you'll see this is a 100 megahertz scope and it can do 1 gigasample per second. So it's basically taking one sample every nanosecond. So the bandwidth refers to the analog front end of this scope. So inside this scope is a bunch of analog circuitry that's doing some filtering and signal conditioning before the signal actually gets digitized. So all of those analog components are limited with rise time, and that basically determines the highest frequency content that the analog side of the scope is capable of measuring. So 100 megahertz actually refers to the minus 3 dB point of the analog portion of the scope. So at minus 3 decibels, if you were to be feeding in 100 megahertz 1 volt peak to peak sine wave, what you would end up actually getting on the display is about 700 millivolts. So it's going to attenuate your signal by about 3 dB. Now the second value, the 1 gigasample per second, that refers to the sample rate of the analog to digital converters. So how often the analog signal gets quantized into a digital quantity, which is what's being used to actually display these points. So now back to why the clock looks like a sine wave. So if you remember Fourier analysis, basically Fourier analysis says that any signal in the world is actually an infinite sum of sine waves, just at varying amplitudes and frequencies. So you can create square waves, triangle waves, all that just by adding up a bunch of sine waves at different frequencies. So every signal is going to have a fundamental frequency, but then it's also going to contain higher frequency content, which will give the waveform different characteristics and shapes. So anytime you have a fast edge, like in the case of a square wave, that fast rising edge contains a lot of high frequency content. And given that this is just a 100 megahertz scope, even though this is a 54 megahertz sine wave here, or a 54 megahertz clock, the frequency content that describes these fast edge transitions could be well into the hundreds of megahertz, maybe even gigahertz. And that's where the problem is with using a low bandwidth scope, is you may be able to see the fundamental frequency of the signal you're looking at, but it's not going to allow you to see the higher frequency content, which is sometimes just as important, particularly when you're looking at harmonics from power supplies, or if you're working with high-speed digital signals. You're, like for example, working with memory, you might be in the hundreds of megahertz, but the rise times of the clock and the data are so fast that it contains frequency content that could be at 5 or even close to 10 gigahertz. So just for fun, let's bring out a different scope and see what this same waveform looks like, but with a higher bandwidth and sample rate. Here's a 4 gigahertz 20 gigasample scope, which is far beyond the capabilities of this scope. But as you can see, they're telling two very different stories. Here we have a 54 megahertz sine wave, and in reality we actually have this 54 megahertz square wave, and you can see the ringing both at the rising and falling edge of the clock. So this scope tells a much better picture of what's going on. Now 4 gigahertz is overkill for a 54 megahertz signal, but the general rule of thumb is you want your bandwidth to be about 5 times the amount of the signal you're trying to look at, particularly for square waves, because the square waves contain a lot of high frequency content near these transitions. One way of looking at the frequency content within a signal is to do a fast Fourier transform. So if we want to see what kind of frequencies are contained in here, we can pull up the FFT. So here's our clock frequency in the time domain. Can't really see what's going on because it's all smushed together. But in this plot here, you can see the fundamental frequency at 54 megahertz. Not sure if you can read this axis here, but it's right between 50 and 60 megahertz. And this FFT plot is spanning from 1 megahertz all the way up to 2 gigahertz. So you can see in a 54 megahertz clock, we actually have frequency content up to well into the gigahertz. And if you're familiar with square waves, you're going to have frequency content at odd multiples of the fundamental. So there's a lot going on here, but when you really get into PCB design, particularly working with high-speed digital signals, this is the kind of stuff that ends up becoming a problem. So one final thing I want to talk about is oscilloscope probes. Now, probes also introduce bandwidth limitations, and they're also going, depending on if you're using a passive probe or an active probe, like this here is a passive probe. What I'm using on this scope is an active differential probe, but probes will introduce their own loading characteristics, and they also have their own bandwidth limitations. So obviously to look at this high frequency content, you need a probe capable of measuring well into the gigahertz, not just the scope. And then also differential probes, which nowadays, particularly with high-speed circuitry, signals tend to be differential, and trying to use regular oscilloscope probes to measure those can be done, but what you end up having to do is use 2 probes and use a math function to subtract one measurement from the other. Thanks for watching, and I hope you found this video helpful. Make sure you stick around to check out the next video in this series.